Hi folks, we're going to take a look at page 221, number 24. So they give us a box with a square base and no top, must have a volume of 10,000 centimeters cubed, and they want us to determine the dimensions of the box that minimizes the amount of material used. Okay, and we'll talk about the other condition that they give us. Okay, so first of all, I'm dealing with a square based box. So when I draw this, I kind of want to make sure that I don't make it look like a cube. Isn't necessarily a cube. Okay, but it does have a square base, okay, which means that these two sides are the same. I'll call them both x, and the height is not necessarily the same. Okay, so we know that the volume is 10,000 centimeters cubed, and what we're trying to do is we're trying to minimize the amount of material used, so that that refers to the surface area. Okay, so here it's an open top box, so I don't include the top part. So when I'm calculating the area, I only have an x squared as the base, okay, as opposed to two of them. And here, since it's square based, all four sides are the same. So plus 4 times hx. Okay. Now here, as we've come across quite a few times, we've got a function to represent what we want to minimize, but it's got two variables. So we'll use that one of the constraints given to hopefully write one variable in terms of the other. Okay, so we have the volume, which would be the area of the base times the height. So x squared h is equal to 10,000. And so here it makes a lot more sense to solve for h, since it'll avoid having to take a square root to replace that x value. So I'm going to isolate h, 10,000 over x squared. And so now let's put that into our equation. X squared plus 4 times 10,000 over x squared for h times x. And that simplifies to x squared plus 40,000, and that x cancels out with one of the ones in the denominator, so I'm just left with this for my area. Now the other constraint that's given is that the smallest dimension in any direction is 5 centimeters. Now that's going to come into play first of all because of the x's here, because those are my variables in my function, so I know that x is going to have to be greater than or equal to 5, but we also have to keep in mind when we get our answer to make sure that h is also greater than or equal to 5. Okay, so we need to keep this in mind. Okay, so now we have our model in terms of one variable. We have our constraint. Next step is to do the calculus to determine the critical points. Okay, so we take the derivative here. So we've got 2x, and here think of this as 40,000 times x to the minus 1. So try to avoid using the quotient rule here. So derivative of x to the minus 1 is negative 1. So this will become negative 40,000 times x to the minus 2. Okay, so since we're looking for a critical point, we shall set the derivative equal to 0 and start simplifying the right-hand side. So this becomes 40,000 over x squared, and we're left with a rational equation, which we can solve by multiplying both sides by this denominator. So I'll multiply the left by x squared. I'm still left with 0. Here we're left with 2x cubed minus 40,000, because I've got to make sure I multiply x squared to everything on the right-hand side. Okay, and now this is easy to solve. Bring the 40,000 to the other side, divide by 2. So that's 20,000. Okay, and in order to isolate the x, I have to take the cube root. Okay, now since this is an application question, the expectation is that we're going to approximate our answer. So we'll take the cube root. So 3/3 root of 20,000 is equal to 27.14 approximately. Okay. Now, the first thing I do notice is that it does fall within my constraint. Okay. However, I do need to make sure that this indeed does relate to a minimum value for my area. Otherwise, I'll have to check the endpoint. Okay, we'll see why in a second. I don't think we'll need to check the endpoint, but we'll see when we get there. So first of all, let's take a prime. So we have to test the sign before and after 27.14. Okay, so Let's take this expression for a prime. Okay, so let's pick, I don't know, let's say, I don't know, let's pick 10. Okay, so let's say we've got 2 times 10 minus 40,000 divided by 10 squared, which is 100. Okay, and we've got a negative value. So that's a good start because it's decreasing as we reach, as we're getting toward 27.14. And let's see what happens on the other side. So let's say I pick x equals 30, and we'll put that in here. So 2 times 30 minus 40,000 divided by 30 squared, and that gives us a positive number. Okay, so this does relate to a minimum. Okay, now normally we would be checking the endpoint also. Okay, now notice how I check the min because I don't have a endpoint on the other end. So here I know that it's always decreasing. Okay, because the only other time this can change sign is when the derivative doesn't exist, which is going to be at 0, and 5 is greater than 0. So I know at 5 this function will be will be larger than what it is at 27.14. Sorry, I don't remember what I said before, but this refers to a minimum, not a maximum. Okay, so the other constraint we have to make sure is observed is that h is greater than or equal to 5. So we need to make sure that if this value for x produces a value of h less than 5, then we have a problem. But let's go back and check what the height will be. So remember, 10,000 over x squared. So here the h value would be 10,000 over 27.14 squared. So let's test that out. 10,000 divided by 27.14 squared, and that is 13.58. Okay, so approximately equal to 13.58 centimeters, which does fall within the acceptable parameters. Okay, so now that I've finished the calculus, let me go back and see what they actually are asking me for, and they're asking for the dimensions that minimize the amount of material. So the dimensions here will be the base is x by x, so 27.14 centimeters by 27.14 centimeters, and with a height of 13.58 centimeters. Okay, so that solves our problem. I will just zoom out so that you can get a look at the whole solution at once. Okay, we'll even fix that there. And there we go. That's that problem.